I see Yanjun came up early today. And Bianjing, who are you? Yeah, it's been a while. And Wei Yo, Bing Rui, and Bo Zhi. Oh, hi there, Yunqi. Oh, hi, Tim. And let me see. I think Exit Man is Sheng Wei, right? And Min Hong, hi. And of course, Yu Ting. I think Tim is Yo Ting, right? Yeah, so 边境, you are a little bit mysterious. I still couldn't quite figure out who you are. Yeah, there you go. Hi, Boris. So, you know what, Boris? Many other students today beat you. Hi, Jamal. So I think Jamal has also an English name, Michael. I hope I was correct. And Juan. So this is Yang Zonghuan, right? All right. Okay, so happy to see so many of you turned out. Even after midterm. I hope it's not too traumatic, the midterm weeks. Yeah, good. Okay. So turned out that today the lecture will be relatively light. We'll be introducing network congestion, okay, a little bit more formally. We talked about it already, I think in chapter 1, giving the overview, especially talking about it when we are trying to measure network delay, right? So congestion, the result is usually queuing delay, and the overall end-to-end delay gets long and sometimes unpredictably long. Hi, Jiayou. And so why don't we go over the announcements, okay? For this week, the assignments due will be PA7, quiz number 25, which will take place today. Tomorrow, we'll start from a quiz as well. It's quiz 26. And there'll be 2 more quizzes tomorrow. So tomorrow we have 3 quizzes, okay? Including today's 25. 25 and 26 are more open problem. So those quizzes are to, introduce the intuition behind the mechanisms that we were talking about, congestion control mechanisms. Okay. Now 27, 28 will be more like these quizzes that allow you to exercise finite state machine. Because in the end, we'll also introduce the finite state machine of TCP's congestion control. So 28, 27 are for you to exercise those finite state machines. And guys, sorry to break this to you, exam number 2 is coming up next week, next Thursday. Yeah, I know, don't panic yet. Yes, sorry about that, Jiayou. There are 3 consecutive PAs in 3 consecutive weeks. But you know what? PA5 and PA6 are quite light. They are not exactly challenging. I could have like one PA5 that does both, right? Creating a server that never really stops, right? That's what people are expecting of a server. Running 7 days a week and 24 hours a day. And PA6 is quite straightforward, isn't it? You just add Go to make it concurrent. And that will make the server you're implementing professional. So PA5 and 6 are actually quite straightforward once you get to know the idea a little bit more. Yeah, so PA7, this week's due assignment is new. Okay, I hope that you guys have already started it. It should not be overly challenging, but it's quite different. It will take you some time. And again, the advice is also that in case you had trouble reading through the PDF description, go watch the video. And maybe speed up the video to 1.5 times so that you can see Polly talking real quick and demonstrate, all right? Okay, good. Yeah, so web programming. Yeah, you have like one assignment each week. probably. Yeah, I know that for many of these programming assignment intensive courses, there's probably no longer exams. Yeah, because as you are experiencing as well, right? For our exams, exam 1, 2, and 3, there are sort of technical problems, and there's also programming problems. Programming problems. I know that some of you did very well with the programming problems, but you see also that it takes time. So you cannot do both. But I do see that those who are good at programming and spend more time doing the PA assignments do well there. Okay? And those who prefer technical problems, answering more math problems, do well in that part. So I think based on exam 1, I see somehow a balanced performance. So you can be good at learning the technical things, learning the FSMs, learning the technical contents, but you can also be good at PA. So either way, you should be managed to pass the course. Okay. Yeah, web programming. But you see, programming is such a thing, just like learning a natural language. You just get yourself into the environment and you exercise the syntax a lot, then you get better. And after a while, maybe a year or two, you find that you finally mastered it. Then you have a special skill there. Okay, so stick around, hanging there. Once you get it through, then it's yours. Okay, but if you give up a little bit prematurely, then to better use the time you have already, take advantage of time you have already invested. Try to stick through. Okay. So today we're going to talk about congestion control. You will see on the internet we are controlling the capacity, okay, of the network. If you overuse it, okay, if you send data that's beyond the capacity, it can be worse than having half of the capacity at all. Okay, so sending more does not give you more results. Okay. Yeah, sorry for the traumatic experience there with web programming, but it's a very useful course. So if you guys are shooting for industrial careers, yeah. Yeah, so coming back, similarly, managing your college life. Okay, each of you have also some capacity. If you take more courses than your capacity can sustain, you will see also that productivity drops lower than when you take less courses. You see. So try to discover yourself, how many courses you can take and what kind of courses you can take. Or maybe you should balance the courses you take. Some assignment intensive, some intellectually challenging. You take a combination of them so that you get a balanced use of your brain so that you don't overstress yourself. Okay. And so today, we'll talk about congestion control, but on the internet only. And let me introduce congestion a little bit more formally with a short video.
Principles of congestion control. Now the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion you see a little bit the nature of the congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now, when we're talking about network congestion, congestion is occurring here. Routers. And these are the machines that are in the core of the internet. And the resources that we're exhausting there when congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this: we see packet loss when the buffer overflows, or long delays when there are lots of packet waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing.
And here come the 3 scenarios. The first one, a little bit more straightforward. The video is short.
Scenario 1 is this. Okay, you see here, we have 2 senders, host A and host B, 2 receivers. Okay, so 2 servers receiving requests, I suppose. So 2 senders, 2 receivers. And we do have a link in the middle. The capacity is what? R. There's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops, because it just takes a long time for the packet to go, but they're never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, the more data we send in here, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. When we exceed the link capacity, because there are 2 flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only at best being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay. We don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remains the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Approaching infinity. So the first bad thing you see already, long delay, when we send a lot more data and more than what the network can accommodate.
All right. So that was kind of to refresh your memory when we were talking about delay, right? Queuing delay goes to infinity when we are close to saturating the network capacity. Now, scenario number 2, it gets a little bit complicated. So the video is going to be a little bit longer, about 7 minutes.
And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops. Right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have one packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer process is generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in, because it should definitely contain the amount of data we need to send out, and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. Okay, the scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay? And that goes back and we remove the copy. Right? So this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the sender side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy, and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there receiving the packet sends back acknowledgement and removing the copy of packet here. And you see, at the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here, because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay? While only one copy of it will be arriving at the application layer. So lambda out remained the same as lambda in, but we see here, the lambda in prime, this is going to be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into a already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case.
And now the scenario number 3. You'll be shocked. It can be worse and much worse. So this video, 5 minutes, slightly shorter than scenario 2.
If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning but saturates toward the end, okay? So beyond certain point, the more work you do, you don't get more results. But here, I'm gonna show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. And each of them is generating a flow traveling multiple hops. So this is one hop. This is the second hop for the red flow. Okay. So multiple hops. And yeah, we might run into buffer full situation, therefore we could have packet drops, and therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer, and lambda in prime being the input rate of traffic into the network from the transport layer. Now let's focus on the red flow coming from host A and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing and sometimes increasing faster than lambda in. Now what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay? And as the rate increases, yeah, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, yeah, the red packet is going to come out and enter the second hop. Just like that, blue packet is going to come out and enter, yeah, this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay, so this is already pretty full when the blue packet just arrived. And as the lambda increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full and quickly. Yeah, red packet will be dropped, but blue packet what? Will be dropped even more because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, yeah, the more output we get. But as it approaches half of R, yeah, we see blue flows, blue packets gets dropped a lot. So originally not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower. Okay, then when the lambda in here is small, really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, okay, it's all wasted. Okay? The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. Okay, so the amount of resources we are wasting here could be very high. Okay, so the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So, message here, congestion, really, really bad. But what can we do about it?
Okay, so let's talk about what we can do about it. And you know what? I'm going to start from introducing a quiz. So quiz number 25. Okay, so this is a quiz try to exercise your creative thinking or troubleshooting skill. Okay, so here it goes. Pretend that you are a Uber driver now. Okay, and you are driving particularly this line between the Taipei city center to the airport. Let's suppose one day you're driving a client to the airport and you discover on freeway or highway number 1, okay, there's a bad congestion. Okay. So Q1 here asks, can you give a couple reasons, okay, that you see often on the highway causing congestion? Okay, so this should be general and straightforward. Q2 here is, okay, so being part of a car fleet, a Uber driver fleet, how would you inform your fellow Uber drivers to prevent from coming up on the highway, okay, and maybe suggest them to take some detour? Okay, how do you inform them? Okay, when do you inform them? Okay, so this is an open-end problem. Okay, gather your teammates, or if you cannot find them, think what will be the best solution for you. Okay, so this is an open-end problem, so you'll be given some 10 minutes of time to think about it. Okay, hopefully you find your teammate. yeah, so it seems that quite a few of you have already answered for quiz 25, right? So team 2 here is saying that, hey, maybe there's a car crash. And, well, too many cars go on the highway too fast, causing a congestion, right? So the remedy is to call the fellow drivers and tell them, hey, I can't move. Just don't bother coming. And team 4, lots of people on the highway or car accident, right? Again, call the other drivers. And I think team 4, the other team may add it, right? Yeah, during the holidays. So lots of people might be traveling southbound for vacation, or some traveling northbound for vacation. So team 3, Jiawen's solution is very complete. Wow, there are 4 reasons why there are congestion on highway. Oh, okay, this one is interesting. Look at this. During the weekdays, right? About 8 a.m. to 9 a.m. in the morning, as well as 5 to 6 p.m. during the night. These are what? The rush hours. Yeah. So everyone wants to go home or go to work. So we go on the highway at the same time. And let's see. Yeah, during the long weekend, we go southbound, northbound for vacations. Car accidents, if this is not rush hour, if this is not long weekend, and there's a congestion, chances high that there's a car accident. Oh, yeah, okay, so the other way around for the long weekend, so people going for vacations at the beginning of long weekend, and then coming back from the vacation. Oh, okay, so Jiawen here has 2 solutions, in fact. Okay, one is just to call the fellow drivers, ask them to change routes. The other is, track the degree of congestion through the monitoring system. If the situation is bad, then inform the users through news or radio. Oh, interesting. Yeah, I think when I was still taking taxi a little more frequently, I usually don't do that when I'm driving, but I can see other people try to call the radio station and telling them that, hey, highway number 1, southbound, okay, 20 kilometer to 30 kilometer, there's a backup. And the radio stations will then broadcast and let all the drivers that are tuned in to the radio station know about the congestion. Yeah. So one way, more effective, to tell not just your fellow Uber drivers, but all the taxi drivers in the whole world or in whole Taiwan, is to tell the radio station. Okay, this is great. Team 7, 加油. Lots of cars on the highway or accidents. Okay. Okay, this is very interesting. Look at this. The rainy day sometimes cause congestion, right? Because you cannot see very well whenever there's heavy rain. Okay. Yeah, police broadcasting, that too. I think there's a police radio station. In Mandarin, it's called 警广. Yeah, so they constantly broadcast in case there's accidents or maintenance going on and things like that. Okay. I think nowadays you might see also the congestion level from Google Map. So another way of advising the fellow drivers might be asking them to check out their Google Map. Right? If it's in red color, that segment is probably heavily congested. Yeah, so Team 7 says just call them. Yeah, I think I've taken taxis before where the taxi drivers all kind of have radios among themselves. That's another way of doing it. And you can just, buzz and then talk instead of, needing to type up the phone numbers, which is a little bit more dangerous if you do that as you drive, right? Yeah. Heavy traffic, car accident, national holidays. Yeah, road in repairing. Yeah, in when there are certain lanes under maintenance, or just a big cars or trucks. They somehow drop the goods on the truck, and there are some cleaning crew there trying to pick things up. Call other drivers or send a message. Exactly. Min Hong here says, yeah, holiday traffic, rush hour, accidents, storm, or traffic control. Oh, okay. Yeah, I think, so when I was much younger, friends and I drove out in the middle of the night. Yeah, we get stopped because there's a certain screening and to check whether you drink and drive at the same time. Okay, so there could be some police stop there. They will be checking whether you are driving dangerously. Yeah, traffic stop or a police stop, some sort of control. Just that the case I described, that's usually in the middle of the night. There's not much traffic. But occasionally you see something like this. There's, very, very occasionally, yeah, the main streets, especially I think Zhongshan's north or south roads, in case there are like foreign visitors, important foreign visitors, VVIPs, who are going to the presidential hall to visit the presidents, the police will actually block the roads entirely. Yeah. So then we queued up and wait until the VVIP came through. Inform him to use Google Map. Great. Yeah, before departure. And probably, right, from Google Map, you can see, maybe there's a better route. Inform the police broadcasting services and have your fellow drivers listening to them, right? And use radio walkie-talkie. Team 12 here. Car accident, of course. Construction. And yeah, certain destination being very hot, especially during the holidays or long weekends. Yeah. Call, listen to radio, walkie-talkie. Call and send messages. Car accident, good. So I guess we've kind of converged, right, to the causes of congestions on highways for transporting cars and people. And the way we do it is usually, in the middle of the road after observing it, calling the fellow drivers or calling the radio stations. Anyway, as we observe the conditions, we notify those who might be interested in the information. Okay. I think in the older time, there's another alternative because back in the 1980s, there are still taxi drivers taking clients to the airport without walkie-talkie, without telephone. How would they communicate to the fellow drivers then? Yeah. Okay, so it's hard for them to communicate this information that the network is congested, the highway is congested, right at the time you observe congestion. So the best thing they can do is probably wait until they arrive at the airport, right? And they park the car and then call back to the station. So a delayed notification. So what you guys came up with are mostly raise a flag. Sure. Like driving and raising a flag. Well, hey, I had some other students doing this. Okay, they raise the flag, and in case there are other Uber drivers driving the other direction, observing it, right? As they drive back, they tell the fellow drivers in the station, okay, or taxi drivers in the stations that there's a congestion. So either very elaborated solution. All right, good. So that was how we observe congestion and how we may be able to notify other people about congestion. Okay. In the next video, let's talk about the general approaches people on the internet. Okay, see we could address notification of congestion, and in case of congestion, how we get around the congestion and still taking the clients into the airport. Or in internet's case, taking the data to the destination.
With the scenarios elaborated, you see, particularly in scenario 3, the only solution or the only effective solution to a congestion is to what? To slow down. And therefore, the two key design elements in a congestion control mechanisms are these. First, detecting when a congestion is occurring. Second, notifying the traffic sources that's causing the congestion to slow down. And there are two major approaches allowing us to achieve those. First is called the end-to-end based approach, the other, the network-assisted approach. Now from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting congestion, informing the traffic source to slow down. Network assisted, on the other hand, is asking the routers to do all these work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there is a congestion occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver sending ACK back. And all these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss, or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially a congestion inside the network. So that is, observing from the loss occurring, inferring there's a congestion. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for the packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that network is running into a slight congestion there. Okay, so overall, general mechanisms observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network, in the meantime not being too conservative, too slow sending the data out. And this is actually rather hard to do for the end systems. After all, they are actually at the very edge of the network. Congestion could be happening anywhere inside the network along the path. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss, okay, if there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right, if there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's, increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point And as a result, we begin to see loss and we begin to see the delay increasing drastically. Yeah, that is actually not good. That indicates that we are probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are failing, if we are detecting the signals of congestions, then that's slowed down. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay. Pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. Right? So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side, both at the end systems. Therefore, it implements an end-to-end based congestion control mechanism.
All right, so we have time to that part of the general approaches. We'll talk about the other approach, which is what you guys all came up with, okay? Trying to do notification in the network, okay? All right, there's just one last thing I want to mention before you go. So after we finish introducing the general mechanisms, end-to-end based versus in-network, we'll begin talking about the congestion control in TCP. Okay. As you see also today, in the last 7 minutes, you hear that TCP is taking this end system approach. So we need to guess what is the right sending rate. Okay. Following talking about TCP congestions control way of guessing the sending rate, we'll be working on this quiz, number 26. So it's actually a game show game. We'll be working on it in 2 stages. So you guys will be asked to guess the price of a certain merchandise that I'll bring up tomorrow. Okay, the one who guessed the closest to the price, the true price of the merchandise, will enter the second stage. In the second stage, you will need to call in from the Google Meet and then work with Polly to guess the price of another merchandise. Okay, and the way we'll play is that you have 30 minutes. You can change the price you would like to guess, and Polly will provide hint. If you guess too high, Polly will say too high. Then you can adjust it down. If it's too low, lower than the true price, I will say, oh, too low. Then you can raise your guess until you get it right. All right. So there'll be extra participation points given to the students. Manage to get through stage 1 and get invited into stage 2. And those who guess right within 30 seconds will get extra participation points. Okay, so those who enter stage 2 get 5 extra points. Those who guess right gets 20 extra points. Okay, isn't that exciting? Okay, and you know what? We'll do 2 rounds, so you guys will have 2 opportunities to compete to guess the prices right and exactly right. Extra. Yeah, so tomorrow definitely come. If you manage to guess it right, 20 extra points, that means you don't have to, come to the class, okay, all that much. Or you can, stay silent on Slack for a while. All right, so that's all. Go on to the next lecture. I'll see you tomorrow morning. Yeah, 20. Okay, if you manage to get to stage 2, 5 points. And that's on top of the 5 points quota in the YouTube channel, in-class participation. Yeah, so that's to make it really fun, okay? By participating in this quiz, you would know why TCP adjusts the sending rate that way. All right, good. All right, so let's go. Go to the next lecture, and I'll see you tomorrow morning. And you know what? That's also why we have the Google Meet session. So I think in the future, with the Google Meet session working, I can introduce more interactive game type of quizzes. It'll be a lot more fun. and learning effectively. Goodbye. Bye, guys. Sure, bye-bye. Okay. Yeah, I think learning should be a little bit more fun, shouldn't it? Yeah, let's have fun and learn at the same time. All right? So, see you guys tomorrow, and I'm gonna end the stream.